Hi everybody. Have you heard the newest LLM joke? Why do LLMs love playing hide and seek? Because they confidently tell you they're under the bed while standing in the fridge. Seriously, let's talk about LLM hallucinations. So we want to trust LLMs, but sometimes they just get facts wrong. This video is about one way of detecting this. Actually, it's based on a paper we published in the Transactions on Machine Learning Research linked in the video description. By the way, I'm Kamil, and I'm the first author. Before we dive deeper into the topic, let me introduce my fantastic co-authors.
Hi everybody, I will gamble with a pawn because I like Monte Carlo. Later on, I will talk about numerical quadrature.
Hello. Um, if you were to say our results are not reproducible, then this is not a very reproducible comment. My name is Sina, and I'm going to show you how to reproduce all of our data sets.
Thanks for the intros, folks. So the main thing is we want to know when an LLM hallucinates. To know this, we rely on a concept known as semantic entropy. Semantic entropy was introduced by another research group. See the slide for a link to their great paper. Now, let me recap the concept in case you haven't heard. So the idea is we want to know if an LLM hallucinates. So we ask the same question, the same prompt a number of times. Then we group or cluster answers according to meaning. If the meanings are different, the model likely hallucinates. If they're mostly the same, it likely does not hallucinate. So this is the main insight of the folks that introduced semantic entropy. Now, how does it look like formally? So formally, the semantic entropy of a prompt is the Shannon entropy of the meaning distribution. And the meaning distribution is induced by squashing the distribution of the continuations that the LLM generates for this prompt through some function that assigns meanings to those continuations. Okay, if this sounds too abstract, let me introduce it by using an example. So let's say we query the LLM, what is the capital of France many times. So the prompt is, what is the capital of France? And now it answers Rome or it's Rome or something equivalent 34% of the time. It answers London or equivalent 23% of the time. And it answers Berlin or equivalent 43% of the time. So now what we can do is we construct a probability distribution from these percentages. And the semantic entropy is the Shannon entropy of this distribution, which in this example works out to be more than one actually. So it's obvious it hallucinates. In many practical examples, it will be far less obvious, but we will later see that the method still works. Now, well, the obvious question is, what about efficiency? Because you have to query this LLM many times. And that's a problem because querying an LLM is expensive. So the main contribution of our work is to make this process more efficient, requiring only half the budget in terms of the number of queries to the LLM for the same quality of hallucination detection compared to the original paper. So now the big question is, how did we do it? We turned to Bayesian estimation to improve efficiency. So now let me build up the method that we used in 3 steps. So in the first step, I'm just going to introduce the basics of how beliefs about the entropy can be built up. Then we're going to add probabilities to the equation to improve estimation performance. And finally, I'm going to talk about modeling an unknown number of meanings as opposed to a fixed number of meanings. Okay, so what are the basics? So we have this meaning distribution, which is just the probability of each continuation of each LLM response squashed through the function that assigns meanings to continuations. Now, we use a probabilistic belief about what the meaning distribution is based on limited data. So this is sort of like the Bayesian philosophy in a nutshell. We don't know the distribution of meanings, so we represent it using a probability distribution. Now, for tractability, we use the Dirichlet distribution to represent this belief. Now, a belief about the distribution of meanings induces a belief about its entropy, and then we use the mean and variance of this belief to sort of approximate the value of a semantic entropy. So let me use an example to explain this. So the prompt is, what's the capital of France? Let's say the LLM answered 5 times. It answered Rome twice, London once, and Berlin 2 times. Now we have 5 samples from the meaning distribution M. So what could this distribution be? So we use the Dirichlet distribution, which reflects with a modeling tool over the probability simplex. And we have this probability simplex shown on the right-hand side, which basically says Berlin and Rome are a bit more likely because we've seen them twice, and London is less likely. And now, A sample from a Dirichlet distribution is itself a probability distribution. And so it has an entropy. So we can sample from this Dirichlet many times, and we can compute an entropy each time, and we get a distribution over entropies. And this is the belief age about what the entropy is. It's shown in the lower right-hand corner of the slide, and you can see that the entropy here is, the belief is very, very, like, the typical values of entropy are very large, as you might expect, because this is an example where the model is obviously hallucinating. Okay, so this is how the basics work out. Now, what can we do? What can we do more in terms of improving estimation performance? So we can use sequence probabilities, because an LLM obviously has a softmax layer at the end. As the softmax doesn't just give us sequences, it also gives us the probabilities with which those sequences were generated. And so we can use those probabilities. And if you sort of wonder about how this might be profitable, the easiest example to understand it is if we know that the probability of a sequence is close to 1. Because in that case, we know that the entropy has to be close to 0. So one generation from a very certain model is enough to know that semantic entropy is very, very small. Okay, so how do we do this? Formally, we define this constrained event, and the constrained event says that our belief over the probability of each atom has to be greater than the actual observed probability, which sort of has to hold by logic, basically. And then we condition on that. So it's a probabilistic event, which means the Bayes rule is well defined, so we just use Bayes rule to condition on that. And then instead of having a simplex, we have a truncated simplex. Okay, so then the final extension here is extending the method to an unknown number of meanings. So in the past example, we had 3 meanings. In practice, we don't know ahead of time how many meanings we're going to get. So what we do is we learn a Bayesian prior, which is a discrete distribution over how many meanings typical prompts have. And then if we have seen, for example, 3 different meanings in our sampling process, then what we do is we say, well, it's 3 with probability something, which came out of the Bayes rule, 4 with some probability, 5 with some probability, and so on. Obviously, it cannot be less than 3 because we have already seen 3. So the idea here is basically to use a hierarchical model where we apply Bayes' rule to a discrete distribution which sort of learns the number of meanings that prompts have. You might be asking whether it works. Well, in short, it does work. Here's a representative plot. You can find more plots like that in a paper. In a nutshell, we're almost Pareto optimal, meaning we get better performance for any sampling budget in. I wanted to emphasize that our results were 100% reproducible. Sina will tell you more about the details.
So, like Kamil said, our results are 100% reproducible, both in the narrow sense, meaning that you're going to get the same plot with the same random seed, and also in the statistical sense, meaning that you're going to get qualitatively very similar plots for different random seeds. To make life easier for folks without GPUs, we split the computation into 2 general parts. We have a script that needs a GPU to do LLM generation. And also, we have a Jupyter notebook, which implements our Bayesian algorithm together with some baselines, basically. We have already pre-computed the outputs of the script that needs a GPU so that you don't need to repeat the expensive part of the computation. And here in the video, I will only describe the Jupyter notebook. Please take a look at our GitHub if you want more context about the script. Now, the Jupyter notebook that I talked about takes only about 10 minutes to run on a personal laptop. So hopefully anyone can run it at home. The Jupyter notebook generates all the plots and tables that are included in our paper. One thing that you can do is to change the random seed in that notebook and try to convince yourself that the conclusions that we have in the paper are not going to change. Also, one note is that the function that implements our core estimator is called Bayes underline estimator. which feel free to examine. I encourage anyone to take a look at it. Now, finally, one detail that we previously glossed over was how to do Bayesian inference with truncated Dirichlet distributions. Nicolò will tell you more about this.
Hi again. So we have these integrals for the mean and the variance of the belief about what the semantic entropy is. And the problem is that they're not analytically tractable, so we must find a way to compute them numerically. One in principle could use any quadrature method, really, but the one that we decided to use because it's really easy to use and to implement and also has desirable theoretical properties is the technique called self-normalized importance sampling. For this technique, we use the uniform distribution over the truncated simplex as a proposal distribution. And we do this because it's very easy to sample from this kind of distribution. And we then work out the right weights so that the method converges to the true value in the limit of many samples. The formula is shown on the slide, and over to you, Kamil.
So here is the bottom line. With our Bayesian semantic entropy estimator, you get the same hallucination detection as before, but at about half the cost in samples, twice the efficiency. Basically the 2-for-1 deal of LLM sanity checks. No more standing in the fridge for our LLM.